Hello and welcome to the fourth and final theory session of my teaching course, Forecasting for Data Scientists. This session is about special forecasting problems. What we are going to cover are external variables, intermittent data, hierarchical forecasting, forecasting in retail, interpretability of the forecasts, forecast stability, and some causal inference. So let's start with the first one, the external variables. External variables. So external variables, they can be static or dynamic, and the dynamic ones can be either past measurements or you have some information about the future, right? So let me give you an example, right? So let's say we have here kind of so let's say we have here like a product sales time series for which we want to forecast the future, right? Now we could have one covariate that tells us this is a red t-shirt, right? So you have a covariate that tells you category t-shirt, color red, and this will not change. So this is a static covariate. You could have a dynamic covariate, which could be something like the price of that t-shirt or the promotions that you're running, right? So here is a promotion and here we ran a promotion. And now, of course, well, some of these you could know them in the future. So like if the marketing department tells you, yeah, we're going to run a promotion here and another one here, then you know that. Or calendar effects. You know when the weekends are going to be, you know when the public holidays are going to be, you know when Christmas is going to be, when Easter, when Thanksgiving is going to be. But then there are also covariates where maybe you don't really know their future. And then the question is, well, can I predict the future, right? For example, the weather. Like I could have like a weather covariate in here, kind of sunshine. Is there a lot of sunshine, yes or no? And then I could say, well, maybe I cannot predict this very well, but I can get a weather forecast, an external weather forecast from an external provider, and now I feed that in as a covariate. Or I have covariates, yeah, for which I really don't have any future information, but I know there is something in here that helps me to predict that. And for that one, I only have kind of the past and feed that in. Okay, yeah, static covariates are useful for global models, not for local ones. Of course, if I have only one time series, knowing that this is a red t-shirt is not going to help. But if I have all the t-shirt time series and now I can say this is red, this is green, that can tell you something about how to forecast them together. Yeah, then these dynamic future covariates, the question is this external variable highly predictable, right? So if the future of the series is available, you add it in as a regressor, as I've said, planned promotions, seasonality indicators, weather, calendar effects, and so on. If you have a specialized forecast, like a weather forecast, you add that in. But then for the others, where the future is not so highly predictable, then the question is, does the external variable contain information about the future? And what that means is that, so just because two series are highly correlated, that doesn't mean one series is useful to predict the other, right? So for example, stock prices are very often highly correlated. In certain situations, if there is just a crisis, some external shock, then they all go down, they all go up together. But there's no predictive value in that, right? And that's because the question is there a lag between when an effect is visible in your kind of external indicator time series and in the one that you try to forecast? If there is no lag between in the effect, if it happens together, it's not useful for forecasting. And then the next question is, well, is this lag long enough for the time frame I'm predicting on? right? And another important thing here is that this is not necessarily causality, right? So usually, so let's say you have time series A that causes time series B. Okay, if this is a causal relationship, usually there would be some lag, right? So the idea is, well, between cause and effect, it takes a bit of time. Now the question is, how long does that take? If it takes a couple of seconds, but you are forecasting on a daily scale, probably not good. But also if there is no causality, right? You could have time series C causing both A and B, and now you use A to forecast B. There could be here a lag of 1 hour, and here could be a lag of 5 hours. And then you say, oh, okay, so now I can actually use time series A to forecast B, even though there is no causal relationship. Right? Something like that I see in the well, no, that is a causal relationship. Okay, so you know, something like you C is it's raining, and then A is because of the rain you see, I don't know, no cows are outside. And then B is I want to forecast how much traffic will be on the road. So of course, whether there are cows on the field or not has nothing to do with the traffic, but they're both caused by the same, and one could be visible earlier than the other one. Yeah, and exactly. So this lag needs to be long enough. So if you predict on a daily time series, the lag should be several hours, right? Because the thing is, this daily time series, it's probably some daily average or some daily sum. Well, so to predict an external variable separately, that only makes sense if you can, in this way, model it better or incorporate additional information. Otherwise, you just add the current value and lagged values as additional input, right? So because the problem is, if you do not know exactly how long this lag is in this effect, you should probably put in a couple of lags just to be sure that the right lag is in there. Right? So if I have a daily time series, my lag are 3 days, I put yesterday's value in there, then maybe that's not enough. Maybe I need to put in also the values from 2 days and 3 days ago so that I can see that effect properly. Yeah. And then again, I mean, maybe this maybe this is just a problem that is as difficult to forecast as what you're actually trying to forecast. So then maybe your forecast doesn't improve just because, well, in theory, putting in these lags should help you to of the other variables should help you forecast the variable that you really care about, but maybe the problem is just as difficult to forecast and it doesn't give you any advantage. Okay, so how do I now go about modeling this? So, well, you can just add in these additional variables and potentially their lags in your model, which could be a neural network, a gradient boosted tree. So with a neural network, you need to be a bit more careful because the neural network gets more complex. So while for each additional variable, you get a whole lot new weights, a whole new set of parameters that you need to train. But the gradient boosted trees that can cope with external variables quite well, even if they're not useful, they will not really degrade your performance usually. Foundation models can mostly not handle external variables. A notable exception is Kronos 2 that came out recently. I mean, in that situation, if you have a foundation model that doesn't handle external variables, but you need to use them, you can do something like stacking. So you get the forecast from the foundation model, you feed that into a gradient boosted tree that then also gets covariates as inputs, something like that. Yeah, that's everything about external variables. Next part will be the intermittent data.